Good afternoon. This is going to be a presentation on sports and exercise biomechanics. It'll be assignment 1 in the module by Connor Thomas. So firstly, I will be going through the kinematic and explaining the two different types, explaining the motions, have definitions for each one, also going with sport examples throughout. Then I'll be going through the kinesthetics, explaining that is obviously as well in a little bit more detail, and with sporting examples, and then finally I'll be going on to projectile, explaining that also with some more sporting examples. Everything will have references throughout, and I'll explain them and who they're from as well. So going on to my first slide, linear kinematics. A definition for this would be kinematics is the branch of dynamic concerns with descripting the motion of the bodies. This is by Hay in 1933. Another nice definition that I've found, linear kinematics is the study of the form of sequencing of linear motion with respect to the time. Linear kinematic quantizes and includes scalar quantities of distance and speed. Also includes the vector quantities of displacement, velocity, and acceleration. So this basically explains the distance, speed, and it includes the displacement, velocity, and acceleration. So the triangles, it explains that, and it takes that into account basically. So there are two different types of linear kinematics. There's a linear motion and an angular motion, and I'm going through a little bit more detail of this now. So linear motion, definition I found of this, and also references, as you can see the thing in brackets. Definition for linear motion is a motion along a straight line and therefore can be described mathematically using only one spiral demission. The linear motion can be of two types, uniform linear motions with constant velocity or zero acceleration, non-uniform linear motion with variable velocity and non-zero acceleration. So there's two different types. Rectilinear translation. So basically this is where someone or an object will follow a straight line. So a good sporting example of this would be a 100-meter sprinter. The reason for this is they start at the blocks and they run straight forward and end at the finish line. They don't move their angle, they don't really move their body too much angular wise, they don't change the direction they're going, they just go in a straight line. The next one will be curvilinear translation. This is where someone or an object will follow the path of a curved line. A sporting example of this would be a pole vaulter. They run in a straight line, but when they get up on the pole, they're moving their body around the pole the bar they're trying to go over. Another one of this, a perfect example of this, is a high jumper. So they run up with a curve. So they're curving their body to make sure if they ran at a straight line, they won't be able to get over the bar, at the right angle. So they'd probably just hit over. They wouldn't be able to definitely get as high. So when they curve round, they can get the angle that they want to be able to jump over, and also they angle their back and put their legs over their head. So they can get that angle. Without that angle, they won't be able to get over that bar. So that's why it's called a curvilinear translation, because they follow the curve and an angle. The next slide is angular kinematics. So with angular kinematics, there are lots of different factors, and they all are distance, speed, time, velocity, and acceleration. So I'll be going through a little bit of an example of this with these here now, and just going through them. So angular distance. So it is the sum amount of the angular distance. So basically this means is the path that the body follows and the distance that it follows. So if someone doing a marathon, so that's 26 miles, 24 miles, sorry. If it's someone doing a 400-meter race, doing 400 meters. So that's exactly from start to finish on how far they have traveled and how far the distance is. But with angular displacement, it's a little bit different. It is the difference in starting and finish angles. So basically what this means is if someone's doing a 400-meter race, there's going to be no angle because the start to finish is completely the same. But if someone was doing a 200-meter race, the angle will be different because it is a straight line from the 200-meter line straight to the finish line. So as you can imagine, from an athlete's circle track, it'll be from the 200-meter line and it goes straight through the middle because it is the closest straight line to that finishing point. So that's what that is. Next one is angular speed. So the angular speed, sorry about that. The angular speed is the rate of the body that can move from one angle to another. So basically it is the rate that the body moves. So with the triangle that we normally have, it is distance at the top, speed on the left, and time on the right. Basically you cover the distance, you times speed by time, and that's how you work out the distance of the speed. Now with velocity, angular velocity, it is basically the exact same, but it is taking direction into account. So the definition is the rate of the body that can move from one angle to another, but taking the direction into account. So basically what this is that you go back to your triangle again, but instead of having distance and speed as you would in the last one, you replace distance with displacement and you replace your speed with velocity. So this time you cover your displacement and you do velocity times time. So that's what that explains. And then the last but not least, angular acceleration. The definition of angular acceleration is the rate at which angular velocity changes and you still account the time. So a good way to work this out, or the only way you can work it out, is to work out the average acceleration of an angular acceleration is final velocity minus your initial velocity divided by the time. So it basically is working out how fast you have gone. So a good example of this would probably be a swimmer. Work out your initial or your final velocity at the end of the race, and then work out your initial velocity at the start and divide that by your time, and that's how you work out how quick you're going, basically, and how much you're accelerating. On to the next slide, which now we're going on to linear kinematics. So with kinetics, it's similar to kinetics. It's very similar, but it depends on different factors, and on them factors how much force can basically be produced. So they are human movement, gravity, reaction forces exerted by the ground, friction, and air resistance. So I'm going through the first one. So the first one is human movement. So human movement basically is how that person moves and how much force someone can produce. So if you've got two players going up for a header, it depends on how each person moves. Someone might have a run up. Someone has a run up, they can produce a lot more force. Or it depends. If they're both standing in the same place, one person might have basically better fast twitch muscle fibers, so they're using them fast twitch muscle fibers quicker and can jump higher if they have more muscle mass as well. Gravity, basically it depends on how, maybe mostly on weight really. If you're heavier, you'll probably fall to the floor quicker. If you're using the same sporting example with two people going up for a header in football, you're going to be going, if someone's heavier, or someone's maybe taller, the shorter person might hit the floor first, because maybe the person that's taller can jump higher. So reactions, forces exerted by the ground. Basically, it just depends on what type of conditions you might be in as well. Also, the grip you can get. So if you're on a football pitch and you're not wearing boots, you're not going to get the greatest of friction, you could say, with that ground, and you're not going to use as much force basically. These go nicely to friction as well. Again, if you haven't got the friction, what you're trying to jump off, so if you're a long jumper, if you haven't got the right friction with the your jumping point, you're not going to be able to launch yourself as far as you can. You're not going to get enough force with your foot if the friction ain't there. And then last one, air resistance. So basically air resistance is where you're jumping through the air. If you're wearing a big baggy top, you're gonna you'll float, maybe not float longer. You might stay in the air a little bit longer. But if you're wearing something really tight, you're not gonna when you jump off that starting foot, that jump foot on a long jump. If you're wearing if you've got like a real tight top on, nothing's keeping you up in the air. You've got no air resistance, so the air is under you, and the air will be, even though you can't see it, it's actually keeping you up a little bit. But in a long jump, it might not differ too much because you are, it's only for a couple of seconds. The next one is angular kinesthetics. A definition for this is a couple of pair of forces which are equal in magnitude but opposite in direction are equidistant from the axis of rotation and acts to produce pure rotation, angular angon, Newton's law. A rotating body will continue to turn about its axis of rotation with constant angular. And there's a reference there as well. There are 3 different classes of levers in the body. So as I just said, there are 3 different classes. So class 1 is where the force and the resistance are on opposite sides of the fulcrum. So the fulcrum is in the middle and the force and the resistance are on this exact same side. A good example of this is where the force is on one side of the head, the resistance is on the other side of the cranium, and the fulcrum is in the middle of your head. So that's an example of that. Class 2 is when the resistance and the forces are on the same side of the fulcrum with the resistance closest to the fulcrum. So a good way of this is the fulcrum would be on the bottom of your foot. So like either your back of your ankle or top of your toes. The resistance would be on top of your foot, so the top part of your foot. And then the force would then be on your soleus, so your shin muscles or your shin bones. But your soleus muscle basically. And then going into class 3 is when the resistance and the forces are on the same side of the fulcrum, but the force is applied closest to the fulcrum. So it's the opposite way around now. So it's when the fulcrum is, say, on your elbow joint or by your elbow, where you're on the bottom part of it. The resistance will probably be on the ulna sort of thing, maybe by the ulna and the wrist, and the force will be on your it'll be on your humerus. So the force is closer this time to the fulcrum basically. Moving on, projectile motion and fluid mechanics. So projectile is basically where someone or something, so a object, leaves the ground and moves basically. So a sporting example of this pretty much is basically there will be a long jumper. So basically what this is basically when something leaves the ground, it includes angles, velocity and the height. So that's the 3 things that you have to basically include. So a long jumper runs in a straight line, got his angle, got his velocity and got his height. So he jumps at an angle, so that's one part of it. Your velocity is obviously how much velocity you're making, and you obviously work that out with the triangles, and your height is how high they obviously jump. And then another example of this would obviously be for an object. This would maybe even be a football, tennis, shot put. So the actual objects, so a shot put, where they throw it, the angle, the velocity, and the height they're trying to make, or the football when you're kicking it, when you're doing a pass across the pitch, or then say a tennis serve. With a tennis serve, you're going to want to make it go down. With a ball, you're going to want to make it go up. So it depends really, like the height on a tennis ball, you might want it a certain height, but you want it to go down. But with a shot put, you just want it to keep going up as high as it can. So it depends on the velocity and the angle you want to be throwing at or hitting the ball at, or it depends what type of shot you want to play. If you want to play like a drop shot, you want to make sure the spins on the ball is backwards, so it's going up in the air, but then when it hits it's hitting the ground sooner rather than later. So yeah, that's basically the projectile motion, as you call it. So coming to the end of my presentation now, there's just my reference list, a few references I had throughout that presentation. But thank you very much and I hope you enjoyed.